Welcome, everybody. Morley and I, so I'm Kristan Kershaw and this is Morley Robbins. We are doing a little video today on what Morley's been learning in the last few days, because I love hearing the bits and pieces that he learns, and I think he likes to share them from time to time. So this is designed to be for me to help pull things out of Morley's brain, give his brain a bit of a rest, but also maybe to ask questions and get answers to questions that people are curious on as we go. So tell me what you've learned, Morley.
What did Morley learn today? I don't know why I think that's so funny, but it's like I haven't learned a whole lot, right? Okay, no, it's just I'm not sure people realize. Maybe they do. I don't know, but I don't think they realize how devoted I am to this process of discovery. And every day, 7 days a week, I start around 5:30 sometimes, and read for the better part of 3 hours, and just trying to figure out what the heck's going on. And I have an obvious bias. I think that minerals rule the body, and I have a certain conviction that there's a lot of confusion about the hierarchy of minerals, because I think there is one. And I think that the body was designed to have lots of magnesium and lots of bioavailable copper, and it's made bioavailable because of retinol. And there's something that's very disruptive to that triumvirate of nutrients, which is called iron. And we spent a lot of time in the MAG group talking about that, and then we have a root cause protocol that's devoted to helping people try to increase their magnesium and minerals, increase their bioavailable copper, and this particular enzyme that's so important, called ferroxidase, and try to lower the amount of iron in their body. And so I'm always looking for information that's going to help further clarify what the heck's going on. And just by quirk of fate, one of my students asked a very important question that I initially rebuffed, but then stayed with it and decided to dig into it, which led to a very important article that I was aware of, had read some time ago, but I read it with fresh eyes or new eyes. And then I started to study the footnotes. And that was the oh my God moment. And I stumbled upon this article that is down here at the bottom of the screen by Dr. Williams, Dr. Cartwright, and two of their colleagues. These were a powerhouse team at the University of Utah, starting in the early 40s up until probably the 90s, I would guess. It was probably about a 50-year reign. Dr. Weintraub was a very important figure. He was an MD, PhD who really assembled the team. And this group studied copper metabolism through 20 different studies. And then they had 18 studies on what's called anemia of chronic infection, which is identical to anemia of iron deficiency. And what they basically proved was that there is no anemia of iron deficiency. It's always a copper issue. And of course, that was all swept under the rug after the 1940s and 50s when they published all that, because that didn't fit with the agenda. And this particular study was from 1976, and it's called The Role of Copper in Mitochondrial Iron Metabolism. And I just want to share a couple quick slides and then basically say this is what we're cranking out all the time on the MAG group, and then we're migrating people to a premium community on Patreon right now, because it's a lot of work to do this, and we want to start to get people really in the mindset that we get what we pay for. And while that sounds crass in this very giveaway world, we're trying to do research, and we're trying to expand on this research, and that requires funding. So one of the important tables from that article is called Table 5, and it's looking at the differences between mitochondria that are normal, that have a normal amount of copper, and those that are copper deficient. And there are striking differences in terms of the ability to make heme. It is 50% less in a copper deficient mitochondria than it is in a normal mitochondria. And I think it's important for people to understand that it's actually where heme is made is in the mitochondria, especially inside the mitochondria of what are called the erythroid cells, which are they're the folks that make red blood cells. That's their job. Then we have what's called cytochrome oxidase. Well, that's an enzyme. We know it is complex 4 in the mitochondria today. And it's a copper-dependent enzyme. And you can see the striking difference between activity that's normal and activity that is copper deficient. It's less than 25% of the norm, which is a dramatic difference in terms of its functionality. And what's this complex doing? It's making energy. And if you can't make energy, you can't make the red blood cells. You can't make the heme or the hemoglobin. Then we get to Heme A, which is different than the heme synthesis up here. But Heme A is a very important component of this process. And you can see that it's 25% of the norm when copper's not at proper levels. Then what this complex 4 is really doing is it's consuming oxygen. It's respiring. We breathe as humans and as mammals. We're breathing. Well, that breathing also takes place inside the mitochondria. But what's actually happening there is this oxygen is getting turned into water to release energy molecules. And if you can't do that efficiently and naturally, then you're going to have a problem. And you can see that there's a marked drop between oxygen consumption when there's less copper. And in fact, this would be one way of describing hypoxia. It isn't just a lack of oxygen, it's an inefficiency in being able to use oxygen. Then some of the real striking differences are what the amount of copper is in a normal mitochondria versus a deficient mitochondria. You can see that's a rather striking difference, less than 10%. And yet, look at what happens to iron. When copper goes south, the amount of iron in the mitochondria goes north. That's what's choking the mitochondria, is all that oxygen. And even though we've been trained like circus bears to believe that iron is connected to oxygen, too much iron is overwhelming to the mitochondria. And this is unfortunately where excess iron accumulates, is in the mitochondria. It doesn't accumulate in the cell, despite what the articles might say.
So before we go on to the explanation you're about to give, just to reiterate so that people can really hit home on this, in a normal cell, we would expect that the amount of heme synthesis is at that level of 2.6. But what you're saying is when you're copper deficient, when you don't have enough bioavailable copper, you can't make as many blood cells, right? That's what that first one is telling us. And then the cytochrome oxidase, what you were saying is in the mitochondria, we make energy. And part of that is what we know as complex 4 now, instead of cytochrome oxidase as they've written it, but it's the same thing. So you're saying that around a third-ish, give or take, it's 1/3 of the whole amount to be able to make energy. So if someone's feeling really tired and that they can't make energy, the likelihood is that there's an involvement of not enough copper, right?
That's right. That's right.
Then we continue that to the Heme A aspect and what you were saying, and then feeding into the oxygen aspect. These are all functions of when you're copper deficient, you can't mobilize these aspects. So you're not going to have oxygen transfer. Again, you're not going to make as much energy, right? Your recycling of blood cells, what's going to happen there?
Yeah, it's all going to go south. I mean, the point is there's 3 requirements to make new blood. You got to be able to make energy. You've got to be able to make iron sulfur clusters, which is a particular type of protein that goes into making the heme molecule. And you've got to be able to make heme. Well, copper is essential for all 3 corners of that triangle. And that goes back in research into the 30s. They've known that for a long, long time. But what's happened in the modern era is everything's about iron. Oh, we got to have more iron. Well, if you've got too much iron, but you don't have the ability to use it, it doesn't matter how much iron you keep throwing into the system. If you don't have the copper running these enzymes to use that iron, then it becomes worthless.
Yeah.
And that's why synthase is so important. This is now known in the modern era. This, again, we're talking about something that's 42 years old. There's been a lot of renaming of things, but heme synthase or heme synthesis is now known as ferrochelatase, and ferrochelatase is a little crane that drops an iron into the center of the heme molecule, and that crane operator is copper. They know that for a fact. And so this is a striking distinction about what happens when there's not enough copper.
And we often see people that have hemoglobin levels that are okay-ish, and yet their other iron measures seem to be really low. But then in some who have been especially chronically ill for a long time, their hemoglobin seems to drop down. But what this research is highlighting is the fact if you don't have the bioavailable copper, if you're copper deficient, then that heme synthesis can't happen. So having low hemoglobin is just flagging that you've got low copper at that point anyway.
That's exactly what it's telling us. Yeah, it's a complete revision of what we've been trained to believe in the modern era.
Well, please continue with your next graphic.
Okay. So this is a little bit more esoteric. Well, is that a fly in the background? Got a bug in your system? So what's supposed to happen is this iron exists in two different states. It's in a +3 state and a +2 state. And this is one of the most important steps in the process, is that the iron needs to be turned into a +2 state so it can actually get inside the heme molecule. And what this is saying is that these three pivot points are all copper dependent, but this one over here, this top one is this cytochrome C oxidase. This is just a different way, it's different nomenclature for how to refer to it. And it's also saying that this heme A, we can see that heme A is obviously copper dependent. Well, those two things need to take place in order to turn iron 3 into iron 2. This is called ferric iron. This is called ferrous iron. And this Fe2, this ferrous iron, is a very toxic form of iron that needs to be very carefully handled. That's why I call it the Ferris wheel, because this ferrous iron is what causes all these different symptoms that people have. And this HS is referring to heme synthesis, and it's now known as ferrochelatase. And that copper process is what then drops the iron into the heme so it can go off to become part of hemoglobin. So what this study is doing is going down into a very granular level to explain where the bottlenecks are. It's explaining the difference in the mitochondria at the top, but then it's getting down to a granular level inside the mitochondria. Where's the real bottleneck for making heme and thus hemoglobin? And it's very, very important what's taking place. And it's obviously important that copper needs to be at a significant level to enable this process to occur. Mm. So then I was happy with that. I thought, gee, table 5, figure 2, I'm done, until I got to the summary. And then the summary really encapsulated maybe 5 years worth of work in about 6 or 7 sentences, which was like, it was like manna from on high. So what we've got is some summary points from this article. And what they identify are 4 defects in iron metabolism that have now been delineated. And they are studying this in swine, in pigs. And it turns out that pigs and humans are pretty much identical. In fact, a lot of the people you know, you would say, well, they're pigs, right?
Har, har, har.
But what they're saying here is that impaired synthesis of heme the inability to turn it into from iron 3 and get it into the heme molecule, that's a big bottleneck. Impaired mobilization of iron from the recycling system. What that's saying is that this iron has got to come from somewhere. Well, it comes from a recycling system. And if the recycling system can't let go of it, then we got a problem. And it's got to get into the transferrin. And then the transferrin brings it into the mitochondria as this +3 state. The other source of iron is from the liver. It's called the hepatic cells. And when you see the word parenchymal, it's very hard to say, obviously. What that means is that these are the cells that are the most essence of that particular organ. So these are the liver cells of the livers. They're the most liverish liver cells, okay? And that too needs to get iron into transferrin. Both these systems are getting iron into transferrin so it can get into the mitochondria of these cells in the bone marrow where the heme is actually being made. And then we have impaired absorption of iron from the gastrointestinal tract. And that's a very important bottleneck that we're not going to go into today. But the point is, they were able to identify these were the 4 bottlenecks. And what they've concluded was that 2 copper proteins, the cytochrome oxidase and ceruloplasmin, are involved in the movement of iron in all 4 of these places. And that begins to crystallize why we are so preoccupied with bioavailable copper and the retinol and the magnesium, because it's so important in this overall function so that this picture here can actually work. This is the essence of why people get low blood results and they're misinterpreted. What typically happens is practitioners say, well, your numbers are low, you're anemic, you need more iron. And what this study is clearly saying, is, no, you need more bioavailable copper. That's where the bottleneck has been all along. And this has been growing in importance and in severity ever since 1941, when they started adding iron filings, that's inorganic iron, into the food system. Then in the early 70s, they increased it 50%. Nobody knows what they started with. They actually wanted to triple it in 1969, and there was a 2-year process. And then the FDA finally said, well, we'll just increase it 50%. Scary thought. And at the same time, they were increasing it 50%. They were introducing high fructose corn syrup into the food system. And what does that do? It takes copper out of the equation, which forces more iron storage. So
what about low-fat diet kicked into that too? So no butter. Butter is bad, right?
Right. So you have this conversion, this perfect storm of adding more iron, adding a sweetener that causes copper-iron dysregulation, and the continual process of taking retinol out of the diet, which is essential for making copper bioavailable and regulating iron, especially in the epithelial cells. And what I learned over the weekend, you're asking, what did Morley learn? Morley learned over the weekend is that 80% of cancers take place in the epithelial cells. And what does retinol do? Retinol regulates the epithelial cells. So call me crazy, but maybe it's this lack of retinol thing that's causing all this cancer, that's allowing the iron to build up in the epithelial tissue that's just completely hosing our metabolism.
Wow.
So that's 10 minutes of blah, 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 but it gives you the latest and greatest. And again, this is a study from 1976 from an impeccable team of researchers, copper and iron researchers at the University of Utah. And as I was pointing out to Kristan before we started this, there's a 40-year statute of limitations with medical education. It takes, on average, 40 years for new ideas to become adopted and accepted and become part of the conventional thought. Well, the clock is over. This is 42 years old. And it's time for the world to wake up to how the body really works and stop thinking it's iron when in fact it's a lack of bioavailable copper that's making the iron unusable. It's not functional in the body. And adding more iron to a dysfunctional system is not going to make it any better.
Yeah.
So that's my piece.
Well, and this is the thing. So if people want to learn more, once you've read this slide, watch this video, might be a bit better. Please, I'll put a link with the video, and please go to the website, read some more. You can find plenty in the Magnesium Advocacy Group on Facebook, and also we are doing a tour into Detroit at the end of October. So people can come along and learn more, can meet Morley, can meet a number of the consultants. I will be there all the way from Australia to Detroit. And it gives you a golden opportunity to come and learn with Morley. You can even train to be a consultant with Morley over that weekend. So there'll be more information for people to be able to read there, and keep an eye out for more videos. We'll keep doing these, and we may even do them as Facebook Lives when we can work out that little bit of technology. So
Okay.
Awesome. Well,
thanks so much, Kristan.
No worries.
Appreciate
Okay.
it. Share this.